So, we've seen how you can use infrared to tell us things about molecular structure, right? And we've learned that we can find out about some functional groups from infrared spectroscopy, others not so much. We've seen that, for example, if you have two different alcohols, their infrared spectra are very similar. You can't really tell which is which. Then we saw how mass spectrometry last time gave us a molecular weight. So now two different alcohols, butanol and pentanol, we can distinguish those one from another because they have different molecular weights. But in general, we still don't usually have enough information from those two techniques alone to solve a structure, and certainly not enough information if we have a very complicated organic structure. So now we're going to move on to the third and, for the moment, final technique. There's also ultraviolet spectroscopy, but that's dealt with separately when you get to conjugated systems in around about chapter 18 in 2OB3. So there are many forms of spectroscopy, but this will be the third and final one, and this is nuclear magnetic resonance, or NMR. NMR is far more information-rich than infrared or mass spec. So in general, we might actually be able to solve the structure of a complicated organic compound using NMR only, even though we couldn't do it using infrared and mass spec, even in combination. So there's a lot of information in NMR spectra. That, for you guys, is bad news, right? Infrared was easy. It's got the functional group or it doesn't. Mass spec was easy. It's got a molecular weight, right? And really that's essentially the major piece of information that we can obtain from those two techniques. NMR is different because it's very rich in many different types of information. So we can do NMR of carbon-13, and that's where we're going to start. Notice that the order here is different from the book, but experience suggests that it's in fact more logical to talk about carbon-13. So we have a way to measure carbon atoms in molecules using C13 NMR spectroscopy, and we'll start there, and we'll show you that really you don't have to understand a lot about a carbon NMR spectrum to interpret it. Basically, we're going to sit there and count the number of carbon atoms by recording the spectrum. We'll then backtrack and we'll look a little bit at the theory of the NMR phenomenon. It's not a hugely important part of the course. Usually what happens with theory in NMR is that there's one question in the multiple choice part of the test that deals with the theory. So we're doing this more for the sake of completeness than something that you have to understand in order to actually use NMR spectra to interpret structure. So I want to show you C13 because it's simple. We're going to get one peak in the spectrum for each different carbon atom environment within the molecule. And really that's the major piece of information that we can get from carbon-13 NMR. But we'll then move on to proton NMR. And then we'll see that in proton NMR spectroscopy we get several different pieces of independent information, bits of information that we get, for example, from chemical shift that tell us about the environment of protons, information from recognizing that the technique is quantitative, so it tells us how many protons or hydrogen atoms we have in a particular site. 3 for a methyl group, for example. So we can actually count 1, 2, 3 hydrogens in an environment. They're all the same, ergo we must have a methyl group, for example. So the integration, the position of the signal tells us about the environment of that methyl group, whether it's next to an oxygen or a nitrogen or a chlorine, for example. We get that environmental structural information about functional groups that are close to that methyl group. And then we can count the hydrogens. We can distinguish between a CH3 methyl group, a CH2 methylene, a CH for a methine position. We'll learn about how the protons in proton NMR talk to one another. They recognize the existence of their neighbors. And this gives us a way to count not only that methyl group has 3 protons, but we can also find out how many neighbors there are on the carbon next door. And that gives us connectivity information. And finally, by measuring the extent, the strength of that connectivity signal in the NMR spectrum, we get information about the geometry of the molecule, whether For example, an alkene is cis or trans E or Z. And so in section 4, that's a phenomenon called coupling in proton NMR, and we'll return to do a little bit of the theory of coupling, again for the sake of completeness, and then we'll end up with a few special features of NMR spectra. So all of this is going to take us 3 to 4 of the Sinfonia lectures. We should be just about finished around about the time of the midterm, and I will let you know how much of this stuff exactly will be on the midterm. Okay, so let's look at carbon NMR. So wouldn't it be nice if we had a way to look at each carbon atom in a compound and know its local environment, know whether it was attached to another, only to other carbons, or to oxygens, or to chlorines, and carbon NMR is the way that we do this. I like to say, you know, there's an app for that. We have a machine that we can stick our sample in, a mysterious machine that gives us a spectrum, a carbon-13 nuclear magnetic resonance spectrum that tells us about the number of carbons and their environment. And then in proton NMR, we do essentially the same thing. We look at each hydrogen atom and know its local environment and learn about its neighboring hydrogen atoms. So NMR allows us to do all of those things. So here is an NMR spectrum. We're going to start with very practical, hands-on sort of thing. Here's a spectrum. What can we learn from it? So this is a spectrum of chloropropanol. Propanol, propane, 3 carbon atoms. There's an ol, an OH group, and there's a chlorine group in this molecule. And we're going to sort of work through the process of looking at the carbon NMR and interpreting it and learning about the structure. So you might recognize that there are many isomers of chloropropanol. We can have in a 3-carbon chain, you can have chlorine one end, hydroxy at the other end, and a CH2 in between. Or you can have the chlorine and the alcohol next door, primary alcohol, secondary alkyl chloride, or a primary alkyl chloride and a secondary alcohol, right? So there's several isomers, and for the moment, the carbon NMR is not going to tell us yet which of the isomers we have. But what can we get from the carbon NMR spectrum? First of all, there's a spectrum, and this time it's the opposite of infrared. When things absorb, we get peaks. So the baseline runs along the bottom, and peaks run upwards. Okay? Makes more sense than infrared. Infrared, as we mentioned last week, is sort of traditionally done in the opposite way. The baseline runs along the top, and when things absorb, we get a trough, essentially, as somebody put it very precisely. So here's our baseline. We have an x-axis, which has the weird symbol delta C on it. This is a delta that is not like the delta plus, partial plus, or delta minus that we are now getting used to. This is the axis that's called chemical shift, and we'll explain what that means in a bit. It's measured in, it's unitless. It's measured in parts per million. Okay, we'll see why that is. And we do that just so that the axis is the same, no matter what particular type of NMR spectrometer that we use. It runs in a normal carbon NMR from about 0 to about 200 or 220 parts per million. Every carbon NMR spectrum runs over the same range. All the different carbon nuclei in a molecule, or in most common molecules, lie in this range. Very few in negative numbers, very few above 220 parts per million. So this is just an axis. It's got numbers on it. Don't worry about the numbers. The only thing you need to know is that, like in all spectra, okay, as in infrared spectroscopy, this axis is in fact an energy axis. So it's an energy axis, even though it's in units that don't look like it. But it is in units that give us quite nice numbers, numbers from 0 to 200, right? We don't have powers of 10 or whatever involved in this axis. It's being carefully selected to give us numbers that are easily handled. So along the x-axis, we have energy, and different energies, different carbon nuclei in the molecule absorb. we have a standard in there, a compound called tetramethylsilane, TMS. And that essentially calibrates the spectrum. The definition of our delta scale is that delta 0 is the frequency or the energy at which carbon atoms in tetramethylsilane undergo the NMR phenomenon. We don't know what that is yet, but we'll look at that later. So, we have a standard compound in there, and it's important to recognize that, because if I give you a real-world carbon-13 NMR spectrum to interpret, it may well have that signal at 0 TMS. That's not part of our unknown compound. If I had a penny for every time a student, you give somebody an NMR spectrum and they see a signal at 0, and they go to the table that tells you what sort of carbons come at 0 ppm, and it says carbons attached to silicon, everybody starts to try to solve a structure that's got silicon in it. Okay? Not a good idea, because none of the compounds that I give you in this course, I guarantee you not to give you anything with silicon in it, or phosphorus, or a whole bunch of elements in the periodic table, because most organic compounds contain one of a few elements, right? We've seen that already. They contain carbon and hydrogen, nitrogen and oxygen, sometimes sulfur, okay? Occasionally some things like phosphorus that I won't give you, chlorine, bromine, atoms that we learned to recognize, that we can tell whether chlorine and bromine is there in an unknown compound. How? Mass spec, right? Because they have those signature patterns in the mass spec. Okay. In order to get an NMR spectrum, practically speaking, we have to dissolve the compound in a solvent. We need a solution. This doesn't work well in the solid state, although we'll talk a little bit about that at the very end. The solvent here is deuterated chloroform. We choose that so that we have a solvent that has no hydrogens in it. That allows us to record the proton NMR of the compound at the same time. So the solvent, if it's an organic solvent, it's not relevant if your solvent is deuterated water, D2O, no carbons. But if your solvent has carbon atoms in it, you will get a signal from the solvent. And in this case, we can ignore that as well. So into an NMR tube, we place our sample, the solvent, a little TMS, all those signals we're going to get, and they all come at places that we know. So we can forget about those. Those are not relevant to solving the structure. What else do we see in this chloropropanol sample? We see peaks that tell us, and those are peaks that come from the sample. We see peaks at just over 65 parts per million, mark number 1, peak at 50 parts per million, mark number 2, and a peak at 20 parts per million, mark number 3. So how many carbon atoms are there in this molecule? 3. And it's as easy as that. The basics of carbon NMR, simply that we have a way to count carbon atoms in an unknown compound, right? And you can see that because, of course, all of organic chemistry is to do with carbon, we always have carbon atoms in organic compounds. This is a very useful technique. It's extremely useful to be able to count the carbon atoms in a molecule. What can we do with that information? Well, we've got the mass spec of the compound. We know the molecular weight, right? Now we know, also we might know, for example, that there's an oxygen in there because we've got the infrared spectrum and we see a CO double bond strap. So what we're trying to do in all of this is, in solving the structure, to get ultimately to an unambiguous structure, is to take little steps. First of all, we got the molecular weight. Now what we would like to do is work towards a molecular formula next, right? Molecular formula just tells us how many carbons and hydrogens and oxygens we've got. Okay? Doesn't tell us what functional groups are there or anything. But a molecular formula, and as far as you're concerned, this applies to every problem that you're going to solve in this course, and spectroscopy will continue as an exercise, usually in 2OB3. Okay? What we would like to do is work our way towards a molecular formula, at least, so that we know what sorts of structures are possible. So if we've got the molecular weight, we don't know how many carbons are there, we're kind of stuck. If we got the molecular weight and the number of carbons, and in fact, as we'll see next week through proton NMR, we get the number of hydrogens. I've now got the number of carbons, the number of hydrogens, the total molecular weight, and the difference tells me what other elements must be there. The difference is 16. That means what? Oxygen, right? Difference is 14, nitrogen. So by combining spectroscopic techniques and by applying carbon-13 NMR to problem solving, then we can help our way towards the molecular weight. Often NMR is the most important technique for structure determination, and in carbon NMR, the number of lines equals the number of carbon atoms, but there is one exception, and that is subject to symmetry. So if there's symmetry in the molecule, two carbon atoms in the same environment that are symmetrically related give a signal at the same chemical shift, because chemical shift tells us about environment, and we'll talk about that later. So frequency along the position of the absorption, or the position of the peak, the resonance as it's called, along the x-axis reveals the environment of carbon and hydrogen atoms. In this case, the chemical shift of the 3 carbon atoms in our chloropropanol tells us that we have two carbons with heteroatoms attached and one that doesn't. And NMR, in proton NMR, we talked about multiplicity and connectivity and geometry and so on. So we may still, for a very complicated structure, still need more information. And so in later courses in organic chemistry, you learn about 2D NMR, how we can turn the NMR spectrum into 2 dimensions and learn yet more about the structure. But in all cases, it's the combination of information from several different spectroscopic techniques that's most important. All right. So in NMR, the nuclei of protons and carbon-13, the heavy isotope of carbon, certain other elements and isotopes behave as if they were little tiny bar magnets. Here's a little bit of background to the physics here. When placed in a magnetic field and irradiated with radio frequency energy, and that's the frequency axis, that's the energy axis along the x-axis of the NMR spectrum, the nuclei absorb energies at frequencies that are based on their chemical environment. And we'll talk about how environment controls the energy of absorption of the nuclei. So this is a nuclear phenomenon. In a magnetic field, so in an NMR spectrometer, we have a large magnet. We put a sample in the magnetic field, and we blast it with radio frequency energy. So this is very low energy, radio frequency measured in megahertz, okay, almost the same frequency that you tune to in megahertz on an FM radio, right? So it's sort of really like irradiating it with radio waves and making the molecules or the nuclei excited. Okay? So NMR spectrometer does several things. The absorption is measured. So the absorption of energy. So certain nuclei resonate. They only absorb at specific frequencies, giving rise to very sharp line absorptions in carbon NMR. Okay, here's an NMR spectrometer, a real one. This is actually one of McMaster's NMR spectrometers, 500 megahertz. This is an older machine. We all are trying to get to higher and higher radio frequency, more and more energy, because we get higher and higher sensitivity as we build larger and larger spectrometers. In essence, the spectrometer is a superconducting magnet. That's the big white thing that says Bruker on it. They're the manufacturers of many of the world's NMR spectrometers. So inside that white thing is a superconducting magnet that creates the highest magnetic field possible. Here's the magnetic field marked H0. Okay, so we create a magnetic field. We put our sample in the tube. There's the tube. And we put it into the spectrometer. We have a couple of coils. These are like radio coils. Radio frequency input excites the nuclei, and we measure the energy output with a second coil that is wrapped around the tube. The spectrum is simply a plot, so as we change either the magnetic field or change the radio frequency input, then at certain radio frequencies where the carbon nuclei resonate, we will get absorption. And so we're plotting the signal coming out as a function of the radio frequency input, in other words, as a function of the energy at which we excite it. The rest of this is sort of what all modern machines look like, right? Bohr, that doesn't refer to the fact that you might not be terribly excited by NMR spectroscopy. We put our sample in there, and we have what Bruker has to show, right, which is their beautiful console full of electronics. So a lot of electronics, and of course we have a workstation with a seat with an operator who stares at the screen, and most of what happens in between really these days is kind of magical electronic stuff. Okay? So let's talk about carbon-13 NMR. Carbon-13 accounts for only 1.1% of naturally occurring carbon. We saw that last time, right? We saw how that impacts the mass spectrum of real organic molecules. Carbon-12 has no magnetic spin, so we cannot, 99% of the nuclei that we put into the spectrometer do nothing. We cannot measure their absorption because they don't have spin. They're even-numbered nuclei. Some even-numbered nuclei don't have spin. So without the spin, they don't undergo the radio frequency excitation in the magnetic field. So we get no NMR signal from carbon-12, and that's why it's called carbon-13 NMR, because we can only observe those rare nuclei, 1% of the sample, that have carbon-13. Most C13 NMR spectra consist of a single peak for each unique carbon. We saw that there. We mentioned how the compound is dissolved in a solvent, CdCl3, and the standard tetramethylsilane, that's a silicon atom with 4 methyl groups on it. Notice in tetramethylsilane there's 4 carbons, but they're all equivalent, right? Each of the methyl groups is equivalent to the other methyl group. They all resonate, all absorb at the same frequency because they're chemically equivalent, and so we get a delta value of 0 for all 4 nuclei in TMR. Chemical shift for most solvents is known. CdCl3 at 77 parts per million. And so the remaining signals are from the compound. And in this case, 3 signals are observed. Therefore, there are 3 carbons in the compound. So, how does chemical shift, why do different nuclei in different chemical environments resonate at different frequencies? And we'll get to that in due course. But the key point, the thing to understand, the most important thing to understand here at this point right now is that similar environments in different molecules have similar frequencies. So a carbon bearing an OH group in an alcohol, it doesn't matter whether it's methanol, ethanol, propanol, butanol, cyclohexanol, okay? All carbons bearing hydroxy groups come within a relatively narrow range of chemical shifts. Here's an example from ketones. Aldehydes and ketones, the carbonyl group is always on the left of the spectrum, typically around 200 ppm. Typical range is quite narrow for a carbonyl of a ketone or aldehyde, 190 to 210. So there's an important corollary from this. Saturated alkane methyl groups are the ones furthest to the right. CH3, chemical shift of about 10 to 20, getting down towards the CH3 group in TMS. So the corollary of all of this is that if I see a signal, if I take an unknown compound, record the carbon-13 NMR spectrum, and I see a signal at 200 ppm, what can I deduce? It's an aldehyde or a ketone, right? Because nothing else, no other types of carbons come in that relatively narrow region between 190 and 210 ppm. So we can make a chart of chemical shifts for carbon NMR, or a table. And here is, this type of chart will be on all tests and exams. So here it is, right? C double bond O. Here in red is the carbon in question. A carbon attached to an oxygen with an alkyl or hydrogen attached, an aldehyde or a ketone, comes in this 190 to 210. Here in this chart it says it can go to 220, fine, okay. There are always exceptions, but I will not give you anything in this course that is an exception to them, right? So if you see a signal if I tell you there's a signal in the molecule at 200 ppm, you can take it to the bank as an aldehyde or a ketone. Carboxylic acids, esters, amides. See, they all have relatively fine, narrow range of chemical shifts here. So if I see a signal at 170 ppm in the carbon NMR, I've got a carbonyl group. Is it a ketone or an aldehyde? Probably not, right? Because those guys are 190 or more. Right? So I can't necessarily tell whether I've got an ester or a carboxylic acid or an amide from the carbon NMR. It doesn't tell me everything. What would I do if I knew I had a signal there at 170 ppm? I didn't know what type of carbonyl substituted compound I had. Look at the infrared, right? Now, the infrared stretching frequencies of those CO groups are different, right? And that's the key. Not one thing will ever solve structure. It's a combination approach that works best. Benzene rings, alkenes, nitriles. Notice there's a huge divide here, right around about 100 ppm. Everything to the left of 100, sp or sp2. Everything to the right of 100, all sp3 except for with the exception of the triple bonds, which are right on the edge, right? So, very handy way to count the carbons. So not only can we count the carbons, but we can count the number now of sp3 hybridized carbons and the number of sp2 hybridized carbons in the molecule. So we're beginning to gain information. Back to chloropropanol. There was nothing above 100 ppm. So in that spectrum, no sp2 hybridized carbons, right? And so we're learning more and more about what's going on. Methyl groups, as I mentioned, on the far right. So this table of chemical shift you can take to the bank, you can use it in the test. If there's a signal there, then, if there's a signal, for example, at, say, 70 ppm, then you can be fairly confident that that is not a carbon with no heteroatom attached. 70 ppm, you've got an oxygen or a nitrogen or a chlorine attached, right? Electronegative elements on an sp3 hybridized carbon push the chemical shift to larger numbers. Okay, so now let's look at our chloropropanol again. The line at 20 ppm corresponds to the methyl group on the far right, right? So we said that our chart shows that anything around about 20 ppm is a carbon that does not have any electronegative atoms attached. The other two have electronegative atoms, one at 50, that's the CCl carbon, and one at about 65, 68, and that's the carbon bearing the hydroxy group. So, what does this mean? It means that at the very least, this sample of chloropropanol is not one where the chlorine and the oxygen are both on the same atom. Right? In that case, that carbon would be moved by both the chlorine and the oxygen approximately additive down to perhaps 90 parts per million. So, but the question still remains which is which, right? So we're learning more about our compound. We're excluding certain structures. Yeah. The y-axis is just amount of absorption. Yeah. Okay. We don't usually label the y-axis because it is arbitrary. It depends on the amount of compound in the spectrometer, right? So there are really no absolute units for the y-axis. Okay. It's just amount of energy absorbed, right? Which is 0 when you're irradiating with a frequency that doesn't correspond to any of the carbon nuclei, or big when you are. Okay? But it's a good question. So we still want to know which is which, because we can't distinguish 2-chloro, 3-propanol from 3-chloro, 2-propanol, and so on and so forth. So you've really learnt the basics of carbon NMR. We can count the carbons, and we can determine to some extent something about their environment. But one of the great powers of NMR is the ability to play sort of little magnetic billiards. We're not going to get into how things like depth work, but basically we can flip the nuclei, we can let them do things, and then flip them again, and from that we can gain even more information. So I like to call this magnetic billiards, right, where you're bouncing nuclei off one another and they're communicating, and all sorts of interesting little physical magnetic phenomena are happening. So if we play magnetic billiards, we can do a whole variety of experiments. We're only going to look at one, the depth experiment. For those who care, that stands for distortionless enhanced polarization transfer. And now you know a whole lot more, right? It doesn't matter what it stands for. But basically what we do is we play magnetic billiards and we make some of the signals go away and some of the signals stay in place. So what that allows you to do is to essentially get a picture of, in a depth experiment, here's the total carbon NMR at the top. In a depth experiment, we can tune it to only show us carbons in CH3 groups. We can tune it to only show us carbons in CH2 groups, and we can tune it to only show us carbons in CH groups. So we can sort, if we choose to, we can sort the carbon NMR spectra by whether they are carbons of metals, methylenes, or methyls. So let's solve this structure now. Remember that the signal to the furthest to the left, right, that's the carbon bearing the hydroxy group. It's got the largest chemical shift. So the hydroxy group is on a methine carbon, a CH carbon, right? So we've got a carbon with a hydrogen bearing the hydroxy group. Yeah? The second one, the one bearing the chlorine, that's a CH2. So we've got a CH2 Cl group. And the third one that doesn't have an electronegative atom attached, that's a CH3 group. Structure solved, right? So you see how depth is extremely useful. We couldn't solve the structure using just the spectrum at the top. Useful information in the carbon, yes, right? We know there's 3 carbon atoms in the molecules. Can you read it from over there? Okay, so we'll just draw it up here. CH3. There's a CH bearing the OH, and there's a CH2 bearing the Cl. Okay? So the carbon NMR alone didn't tell us the structure, but by playing magnetic billiards, we can sort the spectra to tell us which ones are methyls, methylenes, or methyls. So this sample is 1-chloro-2-propanol, the carbon bearing the OH, blah, blah, blah. Okay. And that brings us then to symmetry. So I've told you that you can count the number of carbons in a molecule using carbon-13 NMR, right? And actually it's not quite true, because here's a molecule that has quite a bit of symmetry in it. There's a benzene ring, right? So how many different environments of carbon atoms can we find? There's the one on the benzene ring where the alkyl group is attached. Is that the same as the one on the other benzene ring where the alkyl group is attached? Yes. So those 2 carbons are in the same environment. And chemical shift in carbon NMR tells us about environment. So if chemical shift tells us about environment and the environment's the same in the 2, do we get 2 signals from those 2 carbons? No, right? We get 1. Okay, let's do the next carbon over, the so-called ortho position for those of you who've studied disubstituted benzenes, which is a delight that's coming your way, right? Okay, how about the carbon at the bottom of the left-hand ring? Any other carbons in that ring that are in the same environment? Northeast, right? Yeah? Does it look the same? It doesn't look quite the same. But wait a minute, if we had got to resonance, got further through resonance at the beginning of this lecture, you'd have seen that you can draw resonance structures for the benzene ring by moving the pi electrons around. And if you do that, you move the pi electrons around in a circle, and we'll talk about that next on Tuesday, then those two carbons become equivalent. Okay, so we've got 1, 2. The meta ones are a pair that are equivalent, and the carbon furthest away from the alkyl group. So that benzene ring is going to give us 4 signals. The other benzene ring is going to give us 4 signals. So do we expect to see 8 carbon resonances? The answer is no, because there's a further element of symmetry in this molecule, right? The two benzene rings are equivalent to one another. If I take the molecule, go straight through the center of the sp3 hybridized carbon-carbon bond, and just turn the molecule around, that benzene ring goes to there, the other benzene ring goes exactly to where the first one is. So there are 4 resonances for that. Those are sp2 hybridized carbons, right? So they should be north of 100 ppm. Here's the region, north of 100 ppm. 1, 2, 3, 4 resonances, right? There's a CH2 resonance, okay, and that's way down here at about 30 parts per billion. There's one other signal there, and that's the CH2 group, sp3 hybridized carbon, south of 100 ppm. Only one signal because the two CH2s are equivalent. So if we look at this spectrum, there are only 5 separate carbon signals because of symmetry, and yet the molecule actually contains 14 carbons. So that's a pain, because I told you earlier on I could count the number of carbons in the molecule. That's not quite true. But we have another technique that tells us about the number of carbons in a molecule. What is it? Any votes for infrared? No, very good. Any votes for mass spec? Yay, mass spec. Right. So although mass spec, I told you, was limited, you see, you need all the information to solve the structure. So 14 carbons give only 5 signals in this case. Okay. Oh, it tells you the answer. I thought you guys were on the ball, and it tells you the answer on the next slide. So if we know both numbers, we know the total number of carbon signals in the carbon NMR and the number of carbons in the molecule, and they're not the same, we've still learned something, right? We've learned that there's symmetry, and we've learned the type of symmetry that there must be. Okay. So that's really all there is to carbon NMR, right? It's that simple. You get a spectrum, count the peaks, and that tells you the minimum number of carbons in the molecule. Yeah. Okay, so I told you this was chloropropanol, right? Right at the beginning on slide 1. Right? But we needed to know which isomer it was. Right? Yeah? So I told you it was chloropropanol, right? If you didn't know, how would we solve the structure? We get the mass spec, and we'd see that the molecule contained 1 chlorine because you have an M and an M plus 2 on, right? You know it's got a chlorine in it. The carbon NMR tells us we've got 3 carbons, so we're C3, chlorine. We're going to have some hydrogens, and if you tot it all up, you can't get that excess mass just from hydrogens, right? So you would eventually deduce that there's an oxygen. You get it from the infrared. If you look at the infrared, you're going to see an OH stretch, right? So there's an alcohol. So even if we didn't know what I told you at the beginning, with mass spec and infrared, in combination with carbon NMR, we could solve the structure. All right, so we're just going to start just for a few minutes along the lines of how NMR works. And I was hoping to get through this tonight. We're obviously not going to, but that's fine. Not to panic, all right? We have ways to stay on track. So this is the physics, okay? And if you don't care, you don't care, so we'll just rip through this. So protons and neutrons in the nucleus, individual protons and neutrons have spin. That means they spin, right? What can I say, right? It's physics, right? You want a good explanation of physics? Go to physics class, right? Okay, so if total number of protons and neutrons is odd, then if it's even, sometimes those spins, one clockwise, one anti-clockwise, cancel out, and the nucleus has no spin. Example, carbon-12, right? We couldn't look at carbon-12 NMR because it had no spin. However, whenever we have an odd number of protons and neutrons, we cannot cancel all these plus a half and minus a half spins no matter what. And we end up with nuclei that have a nuclear spin. Proton and carbon-13 is all we're going to worry about here. But we can do NMR on a variety of rare nuclei. Nitrogen-14 has no spin. That's the main isotope of nitrogen. But N15 does. That's heavy nitrogen. Fluorine is fluorine-19, right? It's got an odd number of neutrons plus protons. It's got spin. Phosphorus-31, very useful nucleus to study if you're interested in biological processes, right? ATP has 3 different phosphorus nuclei. You can actually measure ATP in real time in cells, right? By taking a person, a student, whatever, and sticking them in the NMR spectrometer, right? And of course, whole body magnetic resonance imaging is based on putting you in an NMR spectrometer, and we'll talk about that towards the very end. So, if I take that spinning charged nucleus and stick it in a magnetic field, it's like a dynamo, right? How do dynamos work? If I spin the dynamo, right, you have a coil in a magnetic field, you create a current, and you make the light bulb light up, right? You've done that in physics somewhere in school, right? Okay, maybe they don't allow you to do that anymore. Too unsafe, right? The light bulb might break. God forbid. Physics is a hazardous subject. Better ban it from high school. See that in organic chemistry, we are brave and foolish, and we allow you into the labs to do the things that you might have done in high school back in the old days. Right? Okay, so the spinning charge in the nucleus creates I hate this bit. This is where we get into a magnetic moment. Okay, if you're in physics, you understand what a magnetic moment is. The rest of us, not so much, right? Moment. Let's not even spend a moment worrying about a magnetic moment. Okay, we saw in chapter 15 how a dipole moment, oh God, we did, didn't we? Okay, creates a magnetic field. So a magnetic moment creates a magnetic field. Okay, and so we have a little magnet spinning with a north pole and a south pole, and we create little magnetic fields. Okay, and all is well with the world. So normally those little magnetic fields that are created by the individual nuclei are random, but when we put them in a magnetic field and we go to the quantum world, the nuclei line up. We have a quantized situation here. They have to line up rather like a magnet, right? You can line it up. If you let a magnet go, its north pole points to the north pole, right, of the Earth, yeah? There's a second state where I can turn it round and the north pole points to the south pole. And if you let that go in that higher energy state, what happens? The magnet turns around spontaneously. Right? So we create these 2 possible quantized states when we put our sample into the magnetic field, nucleus aligned with the applied magnetic field or against. Like a magnet aligned to the north, the ones aligned with the field are lower in energy. They're marked alpha nuclei, lower in energy, and the beta nuclei aligned against the field have higher energy. So there's now an energy gap between the 2 different spin states. So we create this energy gap. There's delta E, right? Physics again. There's the physicists, right, making it complicated. Big delta meaning a difference in E, meaning energy. So delta E is an energy gap between the alpha and the beta spin states, and they have different energy. So when we blast the sample with our radio frequency at just the right energy, and this is like IR spectroscopy, right? We needed just the right energy to excite the bond to vibrate. Here, at just the right energy, I can flip the nuclear spins from the alpha to the beta state and back again. So we get absorption of energy when we take a sample with spinning nuclei like protons and C13, we put it in the magnetic field. The alpha and beta spin states separate in energy, create an energy gap. I blast with FM 901 or whatever it is. Okay, and when my radio waves have exactly the right energy, I can get excitation. That's absorption, and that is a peak in the NMR spectrum. All right, so the magnetic, so why do all carbon nuclei not resonate at the same frequency? Why do we see ranges of chemical shifts? And that comes about because an actual nucleus in a real molecule is surrounded by circulating electrons. Electrons are negatively charged. They interfere with the magnetic field getting to the nucleus. So it turns out that the chemical shift in carbon and in proton NMR, in fact, the chemical shift of the nucleus, the position along the x-axis in an NMR spectrum, is the result of the electron density around the nucleus. Lots of electrons. The nucleus is shielded in part from the applied magnetic field and resonates at one frequency. Very few electrons around the nucleus, carbon or hydrogen atom. Very little shielding by the electrons, and we resonate at a different frequency. So just before we leave, let's not, okay? So, goes slightly sideways here. All right, so let's think about carbon nuclei, right? Carbon atoms in our chloropropanol, the methyl group, was at a low number of ppms. Does it have anything donating electrons or pulling electrons from it in the methyl group here? Not really, right? The carbon-carbon bond has no dipole. The carbon-hydrogen bonds have no dipole. That carbon is neither delta plus nor delta minus. It's not shielded, it's not de-shielded, so it comes close to 0 ppms. That was the peak on the far right. The other two carbons move further to the left, a higher chemical shift. And they do that because this carbon has a CO polar bond with the oxygen pulling electrons away from it. This carbon is delta plus, and the oxygen is delta minus. Delta plus means there's fewer than normal electrons around the nucleus. De-shielded moves to higher chemical shift. Likewise, the CH2Cl, the carbon-chlorine bond we've already seen, is polar, right? The carbon is delta plus. And so the carbons bearing the oxygen and the chlorine have larger chemical shifts than the methyl group in this NMR spectrum because they have electron withdrawing substituents. We're not really going to worry about why sp2 hybridized carbons come at above 100 ppm. It's in the textbook for anybody who cares, right? It's a result of the pi electrons. So there are logical explanations. The distribution of electrons around the nucleus then is what determines chemical shift. So correspondingly, all alkyl halides have a chemical shift of about 50 ppm in the carbon NMR because all carbon-chlorine bonds are roughly equivalently polar, right? That's what allows you to construct the table. And once you can construct the table, you can solve structures. Okay? Most carbons bearing hydroxy groups, 70 to 80 ppm, right? You can pretty much bank on that range of chemical shift for any carbon in any molecule where there's a hydroxy group. So the corollary of all of this is that in carbon NMR, we can not only count the number of carbons subject to symmetry, but we can also determine their environment. We determine that by looking at their chemical shift and using the table of chemical shifts. The actual physics behind this all has to do with the fact that as we change the functional group, we alter the electron distribution around the carbon nucleus. So for those who care, chemical shift is a consequence of electron distribution, greater or lesser shielding of the nucleus. So it's not worth doing that, right? I don't